is less than the available safe egress time. That is the time before the exits will be blocked by, say, toxic products or high temperature or things like this. So this condition R set is less than less than A set. Is a general condition, and I'll say a couple of words about motivation for this research. All the world now is moving from prescriptive rules or codes for buildings in terms of fire safety to performance-based design, which is a design of building based on their performance in fire conditions. And Russia is, well, with some delay, but starts to catch up with also introducing new laws which make the building designers to prove that the building they're designing is okay in terms of this condition. But it's a very inertial process of making people think differently. And the question which we often ask is, okay, you show this in one particular situation, which you consider as the worst case scenario, but what happens if the situation changes, if you have different fire source or different geometry and things like this? So, as a first step of all uncertainty analysis, we need a sensitivity analysis. And I've done this with a CFAST model for different situations. I thought it would maybe of general interest to see how different parameters affect the result we obtain. We can say that we can perform deterministic analysis of this condition, but this can be insufficient, and uncertainties in the determination of the time that people are evacuating and the time available before untenable conditions will be reached in a compartment should be supplemented by the analysis of all uncertainties, and the source of such uncertainties are intrinsic randomness and variability in physical processes. Fire is a random event. Then deficiencies in our mathematical models, lack of input data, and so on and so forth. So the sensitivity analysis, as we understand it in general case, is it is necessary to establish some credit safety margins, or better to say that uncertainty analysis is necessary to do this, but sensitivity analysis is its part. And the common approach is we vary several model parameters about some baseline scenario and see how significant the change, this results in how significant changes in the output functions. And these output functions can be for fire modeling temperatures, toxic gas concentration, and things, any parameter actually. A more systematic approach, however, is not to make small variation about some baseline scenario, but to apply modern approaches called global sensitivity analysis, which evaluates sensitivity not with respect to some baseline scenario, but over the entire parameter space. In fire-risk studies, the only work on the global sensitivity analysis is, known to me at least, is a recent work by Sofer, published in Fire Safety Journal recently, where they applied the approaches very similar to what will be presented here to Cesare risk. This is a smoke movement model developed by them. In this work, in their work, they studied sensitivity of the maximum temperature in the upper layer and the available safe egress time to 8 input parameters using single zone model. Their model is a single zone. Again, the same questions which were asked on the previous presentation apply to here. When we have short times and people are evacuating, it's normally conditions when we have very strong stratification and two layers. So the objectives are to carry out this global sensitivity analysis based on a Z-zone model Another thing we wanted to see is how this works with multiple rooms. Our geometry is moderately complex. It's either a single room or 3 rooms connected with a long corridor. This is one of the cases which is included in documentation by CFAST, and the experiments are available for this. And finally, a 2-level configuration in which 2 rooms on the lower floor are connected by a vertical vent to a room upstairs. The main output parameters are directly related to asset. This is the time of untenable conditions due to high temperature. Well, the temperature at a given height reaches some value considered as a danger threshold, and loss of visibility, which also affects people trying to evacuate. As the fire model, we used the well-known CFAST model developed at NIST version 6. I think this model is well established now. The only thing, this is the picture taken from their manual. We have 2 layers. The upper layer is a hot layer, the lower layer is a cold layer. We have an opening and the flow into the compartment and out of it. And these 2 layers are connected by a fire plume, which transport the energy and smoke products from the source and the entrained air into the upper layer. And all this is described by the system of equation, from which we can find out all parameters like temperature or composition of lower and upper layers, plus the interface height. We can see how the upper layer grows. So now this is a deterministic model where we put some input parameters and get some results. To make it to make a sensitivity analysis, we run CFAST under the Dakota toolkit, which is the software package developed at Sandia National Laboratories. It's a general purpose engineering package for sensitivity analysis, uncertainty quantifications, things like this. So we run CFAST as an external solver to Dakota. Dakota generates for us stochastic input data for our parameters. Then CFAST calculates each scenario, generating the outputs, the times of untenable conditions due to high temperature and due to visibility. Then we feed this output back into Dakota for statistical analysis. That's how it works, and the results are so we choose parameters and their variation ranges, and then run this repeatedly until we have high enough samples. Okay, so now more to specific things. Analysis. We tried 2 things which are included in Dakota and considered as general or modern global sensitivity analysis. First is the fast screening tool, so-called Morris method, when we have our output depending on several inputs, and we perturb each input by some delta and calculate the difference. And in this case, we obtain the difference in our outputs due to difference in one particular parameter. This is explains one at a time, or more method. But this is not supposed to be a derivative in the sense that these deltas are not considered as small values. And then we have calculate this function in a number of points. I designates the point, and then we can find out the average or modified average, which takes this as a module or absolute value, and then we can calculate the standard deviation. What's the sense of this? The higher the mu or mu star values, the more sensitive our problem is to some particular parameter. And this summing up over the whole